Hello everyone, my name is Lizbeth Peñaloza Velasco. I am a PhD student and I'm going to talk about the shape of a sigma tree. This is a joint work with Arnold Sirigi and Adrian Gonzalez Casanova. Then I'm going to start talking about the seed bank coalescent. It was defined in Blatt et al. At 2016. The block counting process of the seed bank and coalescent is the two-dimensional Markov change, where capital N represents the number of plants at time t, and capital M represents the number of seeds at time t. A small n means that we start with n plants and 0 seeds. This Markov chain has the following transition rate. C1 and C2 are bigger than 0. And if at time t we have I plants and j seeds, the next event can be a coalescent. That means that we lose one plant at rate I2, or we have a deactivation. That means that one plant becomes two seed at rate IC1. Or finally, we can have a reactivation. That means that one seed becomes two plant at rate JC. So for example, here, we start with 7 plants. And then this cross means that one plant becomes two seeds, and the dotted line means that we have a seed. And this other cross means that one seed becomes two plants. So in this time, we have 2 plants and 2 seeds. And if you observe, we can lose one plant only by coalescence or by deactivation. So next, in the same paper, they found that sigma n, the time to the most recent common ancestor, starting with n plants and 0 seeds. That means sigma n is the first time that we have only one individual. The expectation of this time is approximately log n. Then our main result is that the total branch length of the seed bank coalescent is starting with n plants and no seed is equal to the active length plus inactive length, where the active length is equal to the integral from time 0 to sigma n of the number of plants, and the inactive length is equal to the integral from time 0 to sigma n of the number of seeds. We found that the total length of the seed bank coalescent over log n converge in probability to 2 plus 2 times C1 over C2, where the first part corresponds to the active length and the second part, 2 times C1 over C2, correspond to the inactive length. Here we have a picture of the seed bank coalescent tree, where we divide it by 3 parts. The first part is when one plant becomes two seed. So before this time that we call gamma n, we only have coalescence. That is the reason that we call this Kidman phase. And we found that n times gamma n conversion distribution to 2 times x over 1 minus x, where x is a random variable with beta distribution and parameter 1 and parameter 2 times C1. Then the next time that we call theta n is the first time that a seed becomes two plants. And we found that theta n is the order 1 over log n, and the number of plants and the number of seeds in this time is the order log n. More specifically, these symbols means that the probability of theta n is bigger than 1 over log n to the 1 plus epsilon 1 power, and it less than 1 over log n to the 1 minus epsilon 2, but probabilities converge to 1. And the number of seeds at time theta n is less than 2 times C1 plus epsilon 3 times log n, and is bigger than 2 times C1 minus epsilon 4 times log n, but probabilities converge to 1. And finally, the number of plants at this time is bigger than log n to the 1 minus epsilon 5 power and is less than log n to the 1 plus epsilon 6, but probabilities converge to 1. And if you observe, before of this time, we only have coalescence or deactivation. That is the reason that we call this Kidman with frozen phase. So we know that the total length of the Kidman with frozen coalescent over log n conversion probability to 2. That is the intuition about that the active length over log n conversion probability to 2. Because if you observe at this time theta n, we have lost n minus log n plants. Then the intuition of the inactive length is that as we started with 0 seeds, we need to accumulate enough of them. And at time theta n, we have approximately 2 times C1 times log n seeds. And after this time, we need to empty the seed bank. And if you remember, 1 seed becomes 2 plants at rate C2. So that is the intuition that the inactive length over log n converge in probability to 2 times C1 over C2. Finally, we have a kind of simple formula where we use the idea of the Chinese restaurant process, but we start with the number of plants. We start with that number of tables. That means, in this case, times theta n, we have 2 plants. So we start with 2 tables when only 1 customer in each table. So if 1 customer sits in the same table, it means that we have a coalescence. Or if 1 customer opens a new table, it means that 1 plant becomes 2 seeds. So at the end, we have that, in this case, green table and blue table, they have the number of plants that they have not visited the seed bank. And the other 3 tables, purple, gray, and orange, they have the number of plants that they visited the seed bank in some time from 0 to time theta n. Then, thanks to Watterson's papers, we found this simple formula, where is the probability of where OI is the number of all blocks of size I, and RI are the number of the recent blocks of size I. This probability is given the number of plants at time theta n. And they have to satisfy this condition, where this means this equality. And finally, this is the both papers that I mentioned. And if you want to read more about our work, you can find our paper in this link, the archive web page. Or if you have some questions, you can ask in the live session that will be on August 25th. Thank you so much.